Number 3, using the steps on how to graph a function, let's graph this one. So what they're first giving us is the first derivative. So what we're doing is just starting from the first derivative and trying to get then the second and seeing what the graph looks like from all of that. Well, since we're already given our first derivative, let's go ahead and set it equal to 0. We can solve it on out. So 0 is equal to x squared minus 2x times x minus 5 squared. It's already factored. So we can set x squared minus 2x equal to 0 and x minus 5 squared equal to 0. So that's x times x minus 2. So we get x equals 0 and x equals 2. So our critical points, x equals 0 and 2. And then also on the other side, if we go, obviously it's x minus 5 times x minus 5, and we're just going to get x equals 5. So we get 3 critical points for our graph. For our points of inflection, let's look at our second derivative. So y double prime is going to equal the first times the derivative of the second. So that'll be a 2 times x minus 5 times 1. So first times the derivative of the second plus the second times the derivative of the first, which is just 2x minus 2. Okay, let's go through and clean this up just a little bit. So y double prime, let's say, I'm going to write that as 2x minus 10, that second part right here, times x squared minus 2x plus 2x minus 2 times x minus 5 squared. Okay, so we want to go through and set this equal to 0 and see what we can come up with. And honestly, since there's several terms in here, we're pretty much just going to have to multiply all this out. You know, go ahead and FOIL these two together, square that out, then FOIL those two together. So I don't know, if you guys are comfortable, what I might do is just pause this video, go ahead and get all that out, and let's just come back, and I'm going to give you guys the actual function of what the second derivative is by the time I set it equal to 0. Okay? So if, in other words, if I multiplied all this out, I'll come back and I'll write this down for you. Okay, so here's the second derivative. Now it's equal to 0. And honestly, solving this, it's not going to be pretty. One of the easiest, let me just go ahead and give you some values here. We have, when this set's equal to 0, we get our points of inflection to be 0.78 and an x value of 3.22. Okay. So what you could have done easily is just graph that truthfully, just graph that on your graphing calculator and just look for the x-intercepts. Just have it tell it to you that way. But x is equal to 0.78 and also x is equal to 3.22. Okay, so let's come in here. Let's give us some more room just for a second. And we want to, I'll go ahead and leave this, take this off of here for just a second. But we're going to go through here and get our points where we're going to see about the intervals of increasing, decreasing, and then of concavity by testing in the first and second derivative. So in the first derivative, we'll test 0 against 2 and against 5. In the second derivative, we're going to test 0.78 and 3.22. So it looks like great numbers would be negative 1, 1, 3, and 6. Great numbers here would be 0, 1, and 4. Okay, if I easily plug in 0 into, remember this is my second derivative right there, all cleaned up. If I plug in 0 right there, it comes out to be negative 50, so that's obviously negative. If I plug in 1, you just look at the coefficients. So 4 minus 36 is negative 32 plus 90 and then minus 50. So obviously it's going to come out positive. And then 4, it's going to come out. It's going to come out to be negative. Oh, and then I forgot one last thing I was going to show you guys. I forgot that we actually have one more value. I had it written down and I didn't even pay attention to my own handwriting. We actually have one more point of inflection. I erased all that, but we also have one at 5 as well. Okay, and we test that in there and we go with, like, let's say x equals 6, then it's going to be positive. Okay, so there's just be another one right there. Okay, and then on our first derivative, when we're going to go increasing to decreasing, we're just going to plug it back into our original function. You really don't need to worry much about this back part because anything squared is positive, so consider everything coming out of there positive. So we just need to focus on this first part. So negative 1 squared minus 2 times negative 1 obviously is positive. So we're increasing up to 0. After 0, when we plug in 1, 1 minus 2 would be negative. When we plug in 3, 9 minus 6, positive. When we plug in 6, again, still positive. Okay, so if y'all are okay with this, let's go on just to put this information all together. So drawing our graph, we want to go with 1, 2, 3, 4, and 5. We want to go, we're just going to get a rough estimate of the graph here. Okay, so it's saying we're going up to 0. You know, we probably can't even get a y-axis because we don't know what the original function is. Let's just do it like this. Let's do it all with respect to our x values. This will be the easiest way for us. Okay, so if I can almost just draw us a little barrier right here. And we'll call this, how about 0? Okay, all we know is that the graph is increasing up to some point 0. We know it's going to be decreasing all the way. We might cross the x-axis, I'm not sure, but it's decreasing. I'm just going to say draw it down to 2. Okay, and then after 2, we're always increasing. So I know that I'm going to go up. Now let's talk about concavity though. I'm concave down all the way to 0.78, which would be right about there. I'm concave up to 3.22. So coming down, see 1, 2, 3.22. So there's concave up right around there. I'm going to be concave down to 5. So like there. And then concave up the rest of the way. And there's your graph. So I'm going from increasing up to 0, decreasing down to 2, and increasing the rest of the way. But specifically, I'm concave down all the way to 0.78, concave up, back all the way around to 3.22, down, and then up past 5. Okay, so there's another idea of what the graph's going to look like. Let's go to part B. In part B, again, we were given the first derivative. So let's start out by setting it equal to 0. So 0 equals 1 minus cotangent squared x, or cotangent squared theta. And we want to set this equal to 0 and solve for this. So cotangent squared theta is equal to 1. So when does cotangent theta equal plus and minus 1? Well, cotangent theta will equal 1, and then cotangent theta will equal negative 1. Let's focus on this. Cotangent is going to be, the only time it's equal 1 is when you're at pi over 4's multiples of pi over 4. And noticing closely in our interval, we're just going to go from 0 to pi. So from 0 to pi, cotangent specifically is going to be positive 1 just at pi over 4, and negative 1 at, not negative pi over 4, but at 3 pi over 4. Okay, that's the only time it's going to happen in the first interval. Now let's go about finding our second derivative. Oh, by the way, so we can at least label them off. Our critical points are going to be theta is equal to pi over 4, and theta is equal to 3 pi over 4. And then our second derivative. So we need the negative. What is the derivative of cotangent squared? We'll pull down the 2 in front, times cotangent to the first now, theta, and now we have to multiply by the derivative of cotangent, which is a negative cosecant squared theta. Okay, so again, derivative of 1 was just 0, pulled off the minus out front so we can just leave it alone, pulled the 2 down from the exponent, left with 1 inside here, and now took the derivative of the base, which got the cosecant squared theta. Okay, so y double prime as a negative would be positive, so it's 2 cotangent theta cosecant squared theta. And when we set that equal to 0, it's already in factored form. So when does cotangent theta equal 0? And when does cosecant squared theta equal 0? Or cosecant, if we take the square root of both sides, just when cosecant theta is equal to 0. Well, we already decided that cotangent is going to be 0. Basically, this is cosine over sine. So that can only equal 0 only when cosine equals 0. And on that interval, cosine is 0 only at pi over 2. Cosecant, which is 1 over sine, sine is only negative in that interval at 0 and pi, but because we can't equal 0 and pi, we're going to throw that one out. Okay? So our points of inflection, those are going to occur just at theta equal to pi over 2. All right, so let me erase some of this and we'll come right back. Looks like our next step is just to look at our sine charts. So the first one, using the first derivative, we're going to put on there pi over 4 and 3 pi over 4. And then using for our second derivative, what we're going to test with for our points of inflection, we're going to check against pi over 2. Okay, so in that interval from 0 to pi, what we want to test with? Something to the left of pi over 4 could be pi over 6. Between that could be pi over 2. And after 3 pi over 4, it looks like one of the only things left would be 5 pi over 6, without including our endpoints. Okay? And then around pi over 2, that's still in that interval, why don't we just go with pi over 4 and 3 pi over 4. Okay, so when we test these, the first one's in our first derivative, and plug them in, 1 minus the cotangent value of each one of those, we're just going to get the following values. We're going to be decreasing up to pi over 4, increasing past pi over 4, and then decreasing beyond that. Again, just plugging those values in real quick. Just kind of cutting some time down for us. Okay, all the way plugging pi over 4 into my second derivative, we're going to be concave down up to pi over 2, and then concave up past pi over 2. So kind of drawing a general graph. Let's see, we're going to go here. I have an asymptote at x equals 0. I have an asymptote at x equals pi. Okay, and if I get some value, there's a pi over 2 in there. There's pi over 4 and 3 pi over 4. So I know I have a minimum value right here at pi over 4 because I'm going from decreasing to increasing. And again, I don't know if this is above or below the x-axis. Maybe this time we'll just draw it all above. Okay, so I'm going to have a low point there. I know I'm going to have a high point at 3 pi over 4 because I'm going from increasing to decreasing. So I've got a max at 3 pi over 4. I'm concave down to pi over 2. So I'm going to switch concavity somewhere in there. So I'm concave down through here. Then I'm concave. I'm sorry, I've got it backwards. Just one second. That should be a positive, and that one over there should be a negative. I just got it backwards on my notes. Okay, so we should concave up through here and then concave down through there, staying right there in between those two asymptotes. Alrighty, and then our point of inflection is just happening right there at pi over 2, just like we said. Okay, so let's look at example 4.